Have you ever just, stopped for a second and really thought about sight? I mean, how we just look around and see everything. It's something we totally take for granted, right?
Oh, absolutely. It's
Yeah.
so fundamental, but the actual science behind it, often completely invisible. We see.
Exactly. And that's what we're diving into today. Light energy. We're going deep into the really fascinating science behind how we perceive it all.
Yeah, our mission here is to unravel some of those mysteries.
Hmm.
How we see the rules light follows, which are surprisingly elegant and, of course, color, that whole vibrant world.
We want this to be a way for you listening to get those aha moments, connect the dots. We've waded through the notes, the research to kind of give you the essentials in an engaging way.
Hopefully easy to grasp, too.
So yeah, if you're ready to maybe see things a little differently, let's get into it. Okay, first things first. Let's tackle the big one. What is light? And maybe more practically, how does it let us see? Well, anything.
Mm.
That screen you're looking at, the room around you.
Right. So fundamentally, light is a form of energy. It's the energy that stimulates our eyes and gives us the sensation of sight.
Okay, energy. But how does that translate into seeing, say, that chair over there? It's not glowing.
Exactly. Most things aren't luminous. They don't make their own light. We see them because light, maybe from the sun or a lamp, hits the object, bounces off.
Reflects.
Reflects, yes. And those reflected rays travel into our eyes. That signal goes to the brain, and boom, you perceive the chair.
So the chair's just a middleman bouncing light towards us. Makes sense. And light travels fast,
Yes.
right? Like really fast.
Unbelievably fast. In air or in a vacuum-like space, it's zooming along at 3 times 10 to the power of 8 meters per second.
Which is,
300 million meters every single second. It's hard to even wrap your head around.
wow. Okay. A great example of that reflection thing, something that really made it click for me, is the moon. It shines so brightly, but it doesn't make its own light.
Perfect example. It's non-luminous, as you said. We only see it because sunlight travels across space, hits the moon's surface, and then bounces off, reflecting towards Earth.
So the moon's basically acting like a giant dusty mirror for the sun's light,
In essence, yeah. It's a fantastic large-scale demonstration of reflection.
which is a brilliant segue, actually. Let's dive deeper into that whole idea of reflection and mirrors.
Okay, so building on that, reflection is basically what happens when light hits a surface it can't pass through, it hits the boundary and changes direction, bounces off.
It can't go through, so it rebounds. Got it. And there are some specific terms scientists use to describe this interaction precisely, aren't there?
There are. It helps to have a common language.
Yeah.
So the light ray that initially strikes the surface, we call that the incident ray.
Incident coming in. Okay.
The exact spot where it hits the surface is the point of incidence. And then imagine drawing a line perfectly perpendicular to the surface right at that point. That imaginary line is the normal.
Perpendicular, so at a 90-degree angle to the surface.
Okay.
Why the normal?
The normal is crucial because it's our reference line for measuring angles. The angle between that incoming incident ray and the normal line, that's the angle of incidence. We usually call it angle I.
Ah, okay, so not the angle between the light and the surface, but between the light and that perpendicular normal line?
Precisely.
Yeah.
And then, of course, the light bounces off. That outgoing ray is the reflected ray.
Makes sense.
And the angle between that reflected ray and the normal, that's the angle of reflection, angle R.
Incident ray, reflected ray, normal, angle of incidence, angle of reflection. Got it. These terms set the stage for the rules, right? The laws of reflection.
Exactly. And the first law is beautifully simple. It states that the angle of incidence is always equal to the angle of reflection.
Always, no exception.
For reflection off a smooth surface like a mirror, nope, always equal. So if light comes in at, say, a 30-degree angle to the normal,
It bounces off at 30 degrees to the normal on the other side.
precise.
So, following that logic, if the angle of incidence was 45 degrees, the angle of reflection is also 45 degrees. And the total angle between the incoming ray and the outgoing ray would be 45 plus 45, 90 degrees.
You got it. It follows directly.
Okay, what about a trickier case? What if the light hits the mirror dead on, right along that normal line?
Ah, good question. If the light comes in along the normal, the angle between the incident ray and the normal is 0 degrees.
Right. AX 0.
So according to the first law, the angle of reflection ray must also be 0 degrees.
Meaning, it just bounces straight back.
Exactly. It reflects right back along the same path it came in on. Think of throwing a bouncy ball straight down onto the floor. It comes straight back up.
That makes perfect intuitive sense. Okay, that's law one. What's the second law?
The second law is about geometry, about the plane they exist in. It states that the incident ray, the reflected ray, and the normal line all at that point of incidence. They all lie in the same plane.
So they're not like skewed off in different directions three-dimensionally. They all stay flat on one geometric plane.
Correct. It keeps the reflection predictable and two-dimensional in its core geometry.
Okay. Now let's bring this to everyday life. Plane mirrors, the kind we all have. What's the technical definition?
Very simple, really. A plane mirror is just a flat, smooth piece of glass that's been coated on the back, usually with silver or aluminum, to make it reflective. Your bathroom mirror, a dressing table mirror. Those are plane mirrors.
And the images we see in them, they have some really specific, consistent properties, don't they?
They absolutely do. There are like 5 key characteristics you always see with a plane mirror image. First, the image is always erect.
Meaning upright. You don't see yourself upside down.
Correct. Second, the image is virtual.
Virtual. What does that mean practically?
It means you can't project that image onto a screen. If you held up a piece of paper behind the mirror, you wouldn't see your reflection on it. Your brain perceives the image as if it's behind the mirror, but the light rays don't actually converge there.
Ah, okay. So it looks like it's behind the glass, but it's not physically located there. What else?
Third, the image distance equals the object distance. So how far the image appears to be behind the mirror is exactly the same as how far the actual object is in front of the mirror.
So if I stand 2 feet away and my reflection looks like it's 2 feet behind the mirror surface.
Exactly. Fourth, the image is the same size as object. Plane mirrors don't magnify or shrink your reflection.
Right, unlike maybe a makeup mirror or a side view mirror on a car sometimes.
Precisely. Those are often curved mirrors, which follow different rules. And fifth, the characteristic that often trips people up. The image is laterally inverted.
Lateral inversion. Okay, explain that one.
It's the left-right reversal. What's on the left side of the actual object appears to be on the right side in the mirror image, and vice versa.
Ah, yes. Like if I raise my right hand, my reflection looks like it's raising its left hand.
That's it, exactly. That's lateral inversion in action.
You know, the coolest application of this, the one that just blew my mind when I connected the dots, is the word ambulance on the front of emergency vehicles. It's written backwards.
Yes. It looks totally strange head-on, right?
Exactly. Why?
It's pure applied optics. It's written that way specifically because of lateral inversion. Think about the driver ahead of the ambulance. They look in their rearview mirror.
And the laterally inverted reflection of the reversed text reads correctly. Ambulance. Oh, that's brilliant.
Isn't it? So they instantly know what's coming up behind them and can get out of the way. It's a fantastic, life-saving use of a basic physics principle.
That really is genius. Okay, so that brings up the term virtual image again. You contrasted it earlier with real images. Can we clarify that distinction a bit more?
Absolutely. It's a key difference. The main thing, as we said, is projection. Real images can be formed or projected onto a screen. Think of a movie projector, or even a simple pinhole camera creating an image on the back surface.
So the light rays actually converge at a point in space where you can put a screen and see the image.
Exactly. Virtual images, like in our plane mirror, cannot be projected.
Yeah.
The light rays only appear to diverge from a point behind the mirror. They don't actually meet there. Our brain does the work of tracing them back.
So my reflection is definitely virtual. Any other key differences?
Yes. Real images are pretty much always inverted upside down relative to the object. Think of that pinhole camera image again.
Right, it's upside down.
Whereas virtual images, like the one in the plane mirror, are always erect or upright.
Okay, inverted versus erect and location.
Real images form in front of the mirror or aft of the lens. Virtual images always appear to form behind the mirror or before the lens, depending on the setup.
In front versus behind. Okay, that's a much clearer picture now. Real, projectable, inverted, in front, virtual, not projectable, erect, behind.
You've got it.
All right, that's a solid grasp on reflection. Let's shift gears now from how we see images to the very essence of what we often see, color. Color feels intuitive, but the science is, well, it's more involved, isn't it? Let's start with the basics. Primary colors of light. What are they and why primary?
Right. So the primary colors of light are fundamentally any set of 3 colors that if you mix them together in the right proportions, the right intensity, they produce white light.
Mix light itself, not paint.
Crucially, yes,
Yeah.
mixing light. And for human vision, those primary colors are red, green, and blue, RGB.
Red, green, blue. So R plus G plus B light equals white light.
In the right balance, yes.
yeah.
That's the additive primary system. It's the foundation of how things like your phone screen or TV create all the colors you see.
Okay, so if red, green, and blue are primary, what about secondary colors?
Secondary colors are what you get when you mix 2 of the primary colors of light together.
Okay, like what?
So if you mix red light and green light, you get yellow light.
Red plus green equals yellow. Interesting.
Mix green light and blue light, and you get cyan, kind of a greenish blue.
Green plus blue, cyan. Got it.
And if you mix blue light and red light, you get magenta, a sort of purplish pink.
Blue plus red, magenta. Okay. Yellow, cyan, magenta are the secondary colors of light.
Correct. And you often hear about color addition versus color subtraction. Those terms relate directly to this.
How so?
Color addition is what we've just been talking about, adding different colored lights together. That's how displays work, stage lighting. You're adding light sources.
Right, combining beams of light, essentially.
Exactly. Color subtraction, on the other hand, works differently. This is about how objects get their color when they don't produce their own light. It works by absorbing or subtracting certain colors from the light that hits them and reflecting the rest.
Ah, so this is more about pigments, dyes, paints.
Precisely. When you paint a wall red, the paint isn't adding red light. It's absorbing other colors from the ambient white light and reflecting primarily the red wavelengths back to your eye. It subtracts the non-red colors.
This next point was a real eye-opener for me. The idea that the color of an object, like that red paint, isn't actually in the object itself. Can you unpack that? It sounds counterintuitive.
It really does, doesn't it? But it's fundamental. The color you perceive isn't an inherent fixed property of the object. It's actually the result of an interaction.
An interaction between
Two things. First, how the object's surface selectively absorbs some wavelengths of light and reflects others. And second, crucially, the color of the light source that's illuminating the object in the first place.
Wow. Okay, so the object's properties matter, but so does the light hitting it. Color isn't fixed, it's contextual.
In a very real sense, yes. It's your brain's interpretation of the light signals it receives, which depend on both the object and the lighting.
Let's walk through some examples to make this concrete. How does a white object appear white, like this piece of paper?
Okay, white paper under normal white light, which contains all colors, red, green, blue. The paper appears white because its surface reflects all those colors pretty much equally. Red, green, and blue light all bounce off and reach your eye, combining back into white.
So white reflects everything. What about a black object?
A black object is the opposite. It appears black because it absorbs almost all the colors of light that hit it. Very little light is reflected back to your eye.
So black is the absence of reflected light. Makes sense. White reflects all, black absorbs all. What about a colored object, like a red apple?
Right. A red apple appears red under white light because the pigments in its skin are very good at absorbing green and blue light, but they reflect the red light wavelengths.
So white light, R plus G plus B, hits the apple. The apple keeps the G and B and bounces the R back to us. And our brain says, red.
You've got it. That's color subtraction in action.
Okay, let's play with some scenarios then. This is where it gets really interesting. What about a yellow shirt? Why does it look yellow?
Okay, a yellow shirt. Under white light, its dye absorbs the blue wavelengths, but it reflects both red and green light.
And we know red light plus green light looks yellow.
Exactly. So it absorbs blue, reflects red and green, and our brain interprets that R plus G combination as yellow.
Mine's slightly blown again. Okay. What if you had a magenta material that's blue plus red light? What happens if that material absorbs red light? What color would it appear?
Magenta is made of blue and red components. If the material absorbs the red component, the only primary color left for it to reflect is?
Blue. It would look blue.
Correct.
What about green Prussian, but in a room with absolutely no light? Pitch black.
In total darkness, it appears black.
Why black? It's still green, isn't it?
The pigment is still capable of reflecting green light, but if there's no light hitting it in the first place, there's nothing for it to reflect. No light reaches your eye, so you perceive blackness. Color perception requires light.
That really drives home the dependency on the light source.
Yeah.
Okay, tougher one. What if you shine a yellow light, which is red plus green light, onto a blue object? What happens?
Okay, think about the blue object first. Under white light, a blue object looks blue because it primarily absorbs red and green light and reflects blue.
Right. It wants to reflect blue and absorb red and green.
Now, you're shining only yellow light onto it. That yellow light contains only red and green wavelengths. There's no blue light in it at all. So the red light hits the blue object and gets absorbed. The green light hits the blue object and gets absorbed.
Because the blue object absorbs red and green.
Right. So if both components of the incoming yellow light get absorbed, what's left to be reflected?
Nothing. It would look black.
Exactly. A blue object under pure yellow light appears black because the light source doesn't contain the color the object reflects, and the